So our first speaker today is Felix Otto, and he's going to talk about a critical drift diffusion equation of intermittent behavior.
Thank you very much for the invitation. It's a pleasure to be here. We see. I get this to work. Yeah. Okay. So what I'm reporting on is fairly recent work. I started with three then postdocs at Leipzig: Georgiana Chatzi-Georgiou, Peter Morphy, who's still in Leipzig, Lian Wang, and eventually, more recently, a PhD student of mine, Christian Wagner, got involved in this. And so let me set the stage. Let me explain the problem and give one result before I get to the topic I would like to focus on, which is intermittency. So here's the problem we're interested in. So it was already mentioned a bit in Balintot's talk yesterday. So we have a drift diffusion process in RD, eventually R2. It's kind of driven or kicked by thermal noise, Brownian motion, Wiener process W, but it also kind of is advected by a drift B, which we take to be time independent and divergence free, which are two very important structural properties of this problem. And so since this drift is divergence-free, it will have, at least in two space dimensions, closed streamlines with many saddles. So imagine, for instance, a configuration like this. And what you should think of is that that this process tries to follow kind of the streamlines somewhat, and then eventually it gets close to a stagnation point. Then kind of diffusion becomes important and carries it over to another streamline. So that's the interplay of convection and diffusion, and it's in its origin, I think, at least for me, an applied math or physics or fluid dynamics problem, because in a certain sense it explains why in the air we get kind of a much faster effective diffusion than the bare diffusion of something, because the air is in motion, there is something like an underlying drift, and which enhances the diffusion. So the topic, from an applied point, that's the topic of convection-enhanced diffusion, which, for instance, I learned in Andy Maida's course in the 90s. And but then when you start thinking about this, you realize that if you want to give an answer, if you want to understand what the effective behavior is, you realize that it depends very much on the geometry of the flow lines, on the degeneracy of stagnation points, but you would like to say something more generic, and so you're the right audience for this. It's very natural to consider an ensemble, a probability measure of drifts, which means that we're like in Balin's talk, we're back in kind of random environments provided by the drift, and we have two types of noises: thermal noise given by the Wiener process, and quenched noise, environmental noise, given by this drift field B. Okay, so here again is the problem setting. I remind you that we make this very crucial assumption that the drift is independent. In a certain sense, the deterministic part of the equation is an autonomous dynamical system, and it's divergence-free, very much like in Balin's talk. So what's, in a certain sense, very loosely speaking, the most generic way of doing that? The most generic way is by looking at the most decorrelated case, and kind of the most decorrelated case is if you take a B which is completely decorrelated, which means white noise. So let's make the ansatz, which we have to modify in a second. Let's make the ansatz that the ensemble of drifts B is spatial white noise, but that wouldn't be vectorial spatial white noise, wouldn't be divergence-free. So we need to project it onto the divergence-free vector field. In fluid dynamics, that's sometimes called the Lorentz projection. So that's the L2 orthogonal projection onto divergence-free fields. And let's allow ourselves an amplitude, which I will call epsilon. Or more properly defined, you say this random field B is a stationary centered and Gaussian field, and as such it's characterized by its covariance function, which in fact is a tensor because B is a vector field, and it's convenient to describe, always it's convenient to describe the covariance kernel function in terms of its Fourier transform, because then you see non-negativity. And so white noise means essentially it's constant. It doesn't, at least in terms of scaling, it doesn't depend on the size of the wave number, so the modulus of the wave vector. But then you notice this, if you want, Fourier multiplier, which is exactly the projection onto divergence-free fields. So that's the Fourier symbol of the Leray projection. So, but up to this tensorial, non-trivial tensorial structure, it's really the signature of white noise in the sense that you have a flat spectrum. Every mode is equally represented. Okay, so here again I repeat the setting. That's our drift diffusion process with the environment B, this drift field B given as Gaussian. So now I would like to convince you that the two-dimensional case is the most interesting case in terms of dimensions by a scaling argument, by a back-of-the-envelope type of scaling argument, reminding you that the Wiener process has the usual parabolic scaling in law. If you kind of rescale space by a factor of L, you have to speed up time by a factor of L squared. And now we ask the question, when could it be that at least under the annealed law, so both the combined law of the environment and the thermal noise, under which condition could actually this drift diffusion process have the same scaling law? And so what you're confronted with is that white noise, or our white noise type drift, has its own scaling law, which is, yeah, I mean, people have seen the scaling of white noise, wouldn't be surprised if you kind of zoom out, your amplitudes become smaller because of averaging, and the exponent is dimension over 2. So that's the scaling of our environmental noise. And now, if this is to be true, if you want to have diffusive behavior, your drift should scale like velocity, physically speaking. So it should transform like the ratio between how you transform length scales by L and how you transform time scales by L squared. So that gives you L minus 1. And now if you compare these two lines, you see that D equal to 2 is critical. So the interesting case is the two-dimensional case, because then both effects are in resonance. And now kind of the most, kind of the easiest guess is in the 2D case, this object really behaves like an enhanced diffusion. But that is a bit too naive, because it's not well defined. What I wrote down is not well defined, and that's due to the fact that this drift is way too rough to give the equation a meaning, even in the presence of diffusion. And the way you see that is by doing, the first step towards, by looking at the generator, which is the Laplacian plus this drift term. And since the drift is divergence-free, I have two ways of writing the generator, either in this usual way or also in this conservative way. And I will now take the better of the two whenever it suits me to argue that there is still a problem. So B is like white noise. So it has very poor regularity. On the Hölder scale, it has a little bit worse than regularity minus D over 2 minus. So we see again this the scaling factor of D over 2. So if for a moment you look at this equation, that means that that this term here, which has never a better regularity than its factor here, so its regularity should be at least as bad as this one. And now if you solve with some right-hand side, you look at the resolvent equation, you see that the diffusion can only increase this regularity by 2. So the Hölder regularity, the best you can expect for U is 2 minus d over 2. But then you need to make sense of this product. And now I'm looking at the better expression where I have a product of U and B and not the gradient of U and B. And there is kind of a general intuition that you can make sense of such a product only if the function is more regular than the distribution is irregular. In the sense, the sum of these two regularities has to be positive. And again, you find out that this is the case only if d is strictly less than 2. So again, in a certain sense, it's the same scaling argument in a different disguise, which tells you that the two-dimensional case is critical. So that means this problem is too singular from a point of view of SDE and SPD, and you have to regularize it. And kind of the most naive way to do that is just to introduce some cutoff scale for your drift. You cut off the very small scales, you mollify. And conveniently, again, that's done in Fourier space, and it's sufficient to do this in this. How can I get back? Like this. Again, it's keeping the wrong button. Again, you can do that in a very primitive way in Fourier space, just by cutting away all the wave numbers larger than 1, which means all the scales less than 1, and and you can kind of take this cutoff scale, because we haven't non-dimensionalized the problem yet, to be unity without loss of generality. And then epsilon square is a kind of epsilon is a non-dimensional number, which in the applied world is called the Piclet number, which measures the strength of advection and diffusion. Okay, so that's the problem. Let's look at this problem. So here again is the setting, our drift diffusion process with an ensemble of time-independent and divergence-free drifts, characterized, a Gaussian ensemble characterized by this covariance function. And now every realization of B is infinitely smooth. And if you would look at the streamlines, eventually I will tell you that the streamlines are the level sets of the Gaussian free field with a cutoff. You would discover that they, in a certain sense, form a loop soup where there are many order 1 streamlines, but occasionally there is kind of a large a streamline of large diameter. So that's the geometry which, in a certain sense, is given by B. So that's the generic B. Okay, so now the question is coming back to the so our original scaling argument was that that this process should behave in 2 dimensions like a diffusion. So I told you that was too naive, but we can still address the question. And of course, since we did something non-universal to the small length scales, we shouldn't look at small time scales, but we should look at asymptotic time scales or large time scales. And the easiest question to ask is is the mean square displacement of this process, is it behaving in a diffusive way or in a non-diffusive way? So that means we give ourselves a direction in space, but that by isotropy will not matter which one we take, and we look at where the particle is and take the squared moment with respect to the annealed expectations, so both with respect to W and B. And now diffusive scaling would mean that this quantity behaves like in case of Brownian motion, which would be kind of linear in time. Ballistic would mean that it goes like t squared. And now it will perhaps not come as a surprise that to leading order you stay diffusive because that's the scaling, but you get a logarithm because you're in a critical situation and you needed this small scale cutoff, so you break the scaling symmetry and you have to pay with it by logarithm. And so physicists started thinking about this quite some time ago. We like a lot this article here from the 80s, where kind of an informal renormalization group argument is given to argue that indeed that's the diffusivity which you expect. So that's where the physics stood, and then yes.
But can you recover diffusive behavior if T is small enough?
If T is of order 1 or less, this would behave like a diffusion process in a smooth drift field, so essentially constant drift. So on small scales, you get this non-universal behavior which comes from our kind of regularization. So there it would behave like on small time scales, it would behave like a diffusion in a constant drift.
So I was more thinking about T large, but bounded by a large constant depending on K.
So can we come back to this? Because that's perhaps related to the way we approach the problem. Because in a certain sense, we kind of bring in, in the way we prove things, we introduce an artificial infrared cutoff, which sounds a little bit like what you're saying. And once you have this infrared cutoff, then there is an effective diffusivity. And then the question is, how does the effective diffusivity depend on the infrared cutoff? Okay, but that's going ahead. So just to close this introduction, so Balint and Benedict Valco started of course, this is a challenge for mathematics, so one should address this. So they were the first to prove that indeed there is a super diffusive behavior, in the sense that the ratio of the annealed second moment divided by t, which would be constant if it were diffusion, grows at least like a double logarithm. And then quite a bit more recently, Giuseppe with collaborators showed that the physics conjecture is almost true, in the sense that you uncover the square root of the logarithm up to double logarithmic correction, and then the same year we removed this double logarithmic correction on the level of the annealed scaling, and then there's very recent work by Armstrong, Burabe, and Kusi, who showed that this is also true on the quenched level. So, so in that sense, I think now the physics conjecture is well justified. But the story which I would like to tell you in this talk is that in the process of proving this, we came up with some techniques which are related to your question, which actually make accessible different phenomena, which I think are quite interesting, namely intermittency. So that's the story which I would like to tell now. So I would like to kind of tell you here is it's not just kind of this physics conjecture, but there is something else to discover in this process for this type of environment. And I won't make, as you will see, I will make the connection to a stochastic exponential, and in a certain sense, I will make a connection to the multiplicative Gaussian chaos. And I want to explain to you how these two objects come up and how they help us in kind of learning more on this problem. So here is on one slide, I try to kind of capture on one slide the main result on intermittency. This is dense and kind of not as clear-cut as we wish it to be. So we're still trying to improve it. But then I will tell you the story, and the story is, I think, much cleaner and gives you hope that one could get a stronger result. So now I'm a PD analyst, so let me kind of disregard the stochastic process and look at the generator. And look at this parabolic equation, which in a certain sense defines the semi-group of the generator. But let me look at very special initial data. So U is now vector valued, is now kind of, has two components. And let me start with the identity. So what is this process doing? it should be interpreted as Lagrangian coordinates in the sense that it starts from the identity and then deforms into harmonic coordinates at t equal to infinity. So at t equal to 0, it's just the identity. At t equal to infinity, if it were true, I would get a stationary solution which should be interpreted as the harmonic coordinates. And of course, this is, in a certain sense, the kind of the Lagrangian, the position of a particle which started at x when you average with respect to the thermal mass. So in principle, the result which I mentioned before can be expressed in terms of this grad U2. I mean, the super diffusive behavior, the square root of a logarithm comes up when you look at the gradients of these harmonic coordinates. So at the, if you want the Jacobi matrix, the deformation matrix of the gradient, and you see what we proved, that's just a rephrasing of the result on the previous slide. What we proved is that the expectation of the time average, but that's not crucial, that the expectation of the square gradient, and it doesn't matter at which point I evaluate it because it's stationary, blows up like the square root of a logarithm when times become large. So these solutions clearly don't converge. That's not a surprise, but they become larger and larger. Now, what's interesting is that I might still have the hope that if I kind of divide this random variable by its expectation so that I get something that's normalized, that this one might converge. But what we prove is that, in fact, it's not tight. And we prove it in a pretty quantitative way with a specific exponent, which I will hope to explain. Namely, so this is kind of a more quantitative tightness statement. It's telling you that less than half of the expectation of this quantity, which is non-tight, comes from values which are below this expectation to a power which is strictly larger than 1. So the fact that this power is strictly larger than 1 exactly expresses the non-tightness. And the mental picture I would ask you to have in mind is that the solutions of this equation look like this. So this is a 1D rendering of something which should be 2 into 2 dimensions. You start out with the identity, and as time proceeds, this this map becomes more and more corrugated, and it acquires occasionally large jumps, and that's what contributes to the tightness. So in a certain sense, I would like you to think of this evolution as being an evolution in something like a devil's staircase over time. So while this result, of course, is in a certain sense not yet precise enough to make this point, that's the intuition we have. So from a PD point of view, or from a kind of random PD point of view, I find that interesting because you have a simple looking PDE, you have some random coefficient, and the statistics you put in for the random coefficient couldn't be more benign. They're Gaussian. So the least intermittent you may think, but what you get out is something that displays intermittency. So I will tell you in a second in a more precise way why this behavior is related to something which in many areas one calls intermittency. So that's the story which I would like to tell. So now on the next slide.
Sorry.
Yeah.
So I'm just struggling to read your. So you're looking at the expectation on this is an indicator function.
That's an indicator function. So that I'm looking. So that's the random variable, or the family of random variables parameterized by t, and I'm looking at the contribution from low values, but not really low values because I take the expectation which goes to infinity to a power which is strictly larger than 1. So so if this were a tight random variable, if I would put a power slightly larger than 1, I would always get almost all the probability on the right-hand side. But I'm taking something which grows with a specific power of that expectation, and still I only get 1/2 of the contribution. Does that make sense? Okay, so so this is again a somewhat technical statement, but now what I would like to explain on the next slide is that the intuition, or how we get to this statement, is in fact I think pretty clear and intuitive. And just because we don't yet have kind of the best estimates, we cannot translate it in the very clean way. So this slide is supposed to tell you how, in 3 approximation steps, we go from the problem at hand, from these Lagrangian coordinates, to a stochastic exponential. And then I would like to tell you why the stochastic exponential has the feature of the multiplicative Gaussian chaos, where people wouldn't be surprised to see intermittency. So that's the purpose of this slide. So so again, let me write down this on the blackboard, and so we're always looking at this equation with initial data, which are given by the identity. So that's the definition here. And so the first step is to say, and this goes a little bit, I think, in direction of this question. So let's look at the gradient. Let's look at the gradient of this solution at some large time capital T, and let's look at the parabolically associated length scale, which is square root of TL. And now the first statement is, in fact, if you look at this time, you get a good approximation if you, by the solution where you remove the time dependence, but you provide a spatial cutoff to your drift field B. So that's the that's this line. So so the first statement is, in a certain sense, you can replace time by space or by cutoff, where you take this white noise type drift, which had already the UV cutoff of scales 1 or less, and now you introduce an infrared cutoff, an artificial infrared cutoff of scales L and larger. That's the first statement. And then, so some people may recognize that, and in this sense, that's the connection to harmonic coordinates, that it's convenient to rewrite uval as a perturbation of the identity, and the perturbation is what's called the corrector, and that one solves or is characterized by the corrector equation, which here on the level, once you have this large-scale cutoff, is well defined. So that's the first approximation. So that's perhaps not so surprising, that also from the point of view of the process, that as it explores space, it doesn't yet see the very large scales of your drift. And because those are, essentially constant and have a small amplitude, so it, in a certain sense, explores the drift in a dynamical way, so that you may replace the B by its cutoff version. So that's, I think, quite intuitive. So I think at the core is a second approximation, where we take this, what's called the corrector in homogenization, and we say we can construct a proxy by writing down an SDE. So that's a bit strange. That's solving a homogenization problem by stochastic analysis, by Ito calculus. And it only works because we're slightly outside of homogenization. But that's a very powerful approximation. So what's the idea here? So so here's the corrector equation which we would like to understand. So let's take increments with respect to the cutoff scale. Let's adopt an incremental point of view on this equation. So let's apply a little d, which I want to think of as kind of the increment with respect to L to this equation. So then, you know, there's a D which falls here, there's a D which falls here, there would be also D which falls here, neglect this one, so that's some kind of linearization. And now homogenize, replace this drift diffusion equation by its effective behavior, and make the educated guess that the effective diffusivity again has this square root of a logarithmic scaling in L. So that's an ansatz. So the first naive idea would be you obtain a good approximation to your corrector equation if you just integrate this Gaussian ansatz. But that's too naive because we're interested in the gradient quantities. And as is well known in homogenization theory, when you're interested in the gradient of a quantity, you need to correct it by what's called the two-scale correction. So, oops, that brings in this prefactor. So I cannot just say that phi L tilde is equal to phi L prime, which would be if I erase this prefactor, but I have to correct it with the corrector itself. So here is Einstein's summation convention. So that's what's called the two-scale expansion. People who have seen stochastic or any type of homogenization will not be overly surprised about this. So now you see that this indeed has to be interpreted in the Ito sense because it's a multiplicative SDE. So it's a multiplicative SDE, but no, not in time, in kind of the cutoff scale. So that's in a certain sense what I find surprising, that we started out with an SDE in time, and through this procedure, we converted it into an SDE in a cutoff scale. And that's the thing we want to analyze. And now the last approximation step is to say, okay, we're interested in kind of identity plus the gradient of this proxy corrector. And so we have to take the gradient of this SDE. So by Leibniz rule, we get two terms on the product term. We just keep one, namely when the gradient falls on the first term. And that's the last approximation which leads us to stochastic exponential. So the last step is to say that, in fact, when it's about the gradient of this proxy corrector behaves like a stochastic exponential, namely the solution of this Ito equation, where you still use the same driver, which is defined via the white noise and solving this elliptic equation. And so that's the quick connection from the original drift diffusion random environment problem to a stochastic exponential. So now we're in business because here we can compute a lot, and that's exactly what we're going to do. So a stochastic exponential is something nice because you can say a lot. So the interesting thing is, I think, this connection, and once we're here, there's a lot to learn from explicit calculations. So let me do this on the next slide. So here again is is kind of the string of approximations where we end up with a stochastic exponential, which is driven, so the underlying martingale which drives the stochastic exponential is implicitly given by solving this constant coefficient elliptic equation with, however, kind of a time-dependent coefficient, or sorry, an L-dependent coefficient. So now here's the connection to the multiplicative chaos. If this constant would be equal to 1, so it would not depend on L, then the gradient of phi prime, which is the driver, would be one antiderivative of white noise. So it would behave like the Gaussian free field. And then its exponential would be a multiplicative Gaussian chaos. So that's the connection to the multiplicative Gaussian chaos. But in fact, the situation here is slightly more subtle because we're kind of discounting, this is a large number, we're discounting the driver in this way, which leads to the fact that the driver, in fact, instead of being log correlated, as it would be for the Gaussian free field is log-log correlated, but it's still unbounded, so it still has a singular correlation. And as a consequence of this, oops, you get exactly you get the similar phenomena which people are well aware of in case of the multiplicative Gaussian chaos, namely that you get anomalous or inconsistent scaling of moments. So so you can explicitly compute that the second moment of this object grows like this quantity, which grows, becomes large logarithmically. But the fourth moment, which should behave like the square of this, in fact behaves like the cube power of this. So that's intermittency, right? This non-consistent, that's what typically I think is called intermittency, at least in the fluids literature, when moments have different scaling rules.
What is the first moment?
The first moment is 0 because it's, sorry, it's the identity, it's a martingale.
So it's just one.
It's just, well, it's a tensor. So, but up to being a tensor, it's 1.
So what means the second moment, you see?
Well, I mean, I wouldn't. Okay, if you want to put it like this, you could also say that already there you see intermittency, yes?
The expectation of the absolute value.
It's a positive.
So I think so if you okay, I mean there is a general formula of what you put in when you put a p here, and then you see something which on the right hand side is a certain quadratic expression in p. And so, so the fact that it's nonlinear, but it has a quadratic contribution is this intermittency. So in principle, all of these things could be computed. We don't do that because when transferring back, we cannot take this type of information, but we have to take other information because we don't have the estimates to transfer these very clean things over. Okay, here is the bit of numerology which tells you how this arises. So at first it's this is an infinite dimensional SDE in L, but interestingly you can fix the point x, right? It really for fixed x it becomes an individual. So x is just the position in space is just a parameter, which makes it very convenient. So the spatial structure just comes in via the Laplacian. But now it's different from being a standard stochastic exponential because the quantities are tensorial. Those are 2 by 2 matrices, so they don't commute. And so therefore I cannot write down an exponential formula like what's done in the Gaussian multiplicative chaos. So, but still, of course, I can compute everything once I identify the quadratic variation of this object. And by scaling and isotropy, you know that essentially it's given by universal bilinear form on matrices, so a 4 tensor. And you can compute, you can identify it explicitly. You get what's important are these type of contractions, and you get crucial exponents, which then exactly explain this this 3/2, which give this intermittency. So in the end, it's so this is what this is why I think this this martingale approximation, this converting a homogenization problem into an SDE, is promising because it allows you to calculate a lot of things. How am I doing with time?
You have 20 minutes.
20?
20.
Oh, okay. So there's something wrong. Didn't I start at 9? No, I started at
9:15.
9:15. Okay. So thank you. So right. So that's the kind of the main idea. So perhaps let me go back to this slide. So so I think the main step is really kind of saying that this kind of intricate corrector equation can be well approximated by this SDE in L, which is a kind of a strange way of saying that there is no backcoupling of large scales to small scales. And so that's perhaps the main thing which I would like to say a couple of words more on. And that, in a certain sense, was already present in the 22 work. So starting again from what we call the Lagrangian coordinates. Here I put down the proper definition of the truncated drift. So you just again do it in this very brutal way of cutting away the very large scales, which you do on Fourier space by cutting away the very small wave numbers. So we now have a band, but a large band in K-space we're left with. And the claim is that we can pretty well approximate this solution by a solution of this much more manageable and much more explicitly computable SDE. And here's the error result. And here, kind of having a small Peclet number comes to our help. So this is but at this stage I would see that as a strength. So even if the Peclet number is extremely small, so even if the coefficient in front of the drift is small, you retain this kind of intermittent behavior. So it's something which is even present in the simplest case with extremely small Peclet number. And here we capitalize on the fact that the Peclet number is small. Okay, so I have a section on this idea, which we associate to what's called scale-by-scale homogenization. So this connection to the Ito calculus, and but probably I don't have enough time to give you all the detail of this one here. So here comes something you have already heard from Balin's talk. A divergence-free drift can be converted, can be made part of diffusion coefficient, which puts you in this more classical framework of homogenization, of elliptic, of random walkers in random environments. And you do that with help of the stream function psi, which help of which you can write the drift as the rotated gradient. And then you can rewrite the generator as a purely second-order operator with a coefficient matrix, which, however, is Q-symmetric, where the drift is in there. And the stream function is nothing else than the Gaussian free field with both the ultraviolet and the infrared cutoff. So and of course we know that kind of 2 dimensions are critical for the Gaussian free field. So you recover the logarithm there when you look at the second moment of the Gaussian free field. And so here again is a slide on why it's natural to look at the corrector, at the harmonic coordinates, and so that this is the quantity we should look at, because in these coordinates, the original process turns into a martingale. And the main idea is now to derive, in a certain sense, an ODE, at least approximatively, for the effective diffusivity with cutoff. And solving this ODE gives you the formula which you already saw, that lambda L, or lambda L tilde, is equal to the square root of this quantity. And so the fact that we derive an ODE in L means that we do this kind of sequential or incremental or scale-by-scale homogenization. And we're not the first ones to do that. In fact, for the drift problem, that was already the strategy for non-divergence-free drift of Brickman and Kupiainen, and then has been kind of carried through by Hofer and Alain Solis-Snitman. And so we're, in a certain sense, using this idea of a scale-by-scale homogenization which is now explained, but I don't think. So again, how much? Sorry to ask again. So when should I stop?
10, 10, 1, 10, 10. A lot of time for questions.
Okay. So here is so in order to see the idea before really making it infinitesimal, you look at two different, dyadically or geometrically separated cutoff scales. So let's call one L and the other one L plus, and you now do a variance decomposition. So you write your stream function, your Gaussian free field with more scales as the sum of the Gaussian free field with less scales plus an incremental object. And then you look at the difference of two correctors by looking at the difference, the equation, the difference satisfied, which by small algebra becomes this equation. And then essentially you're just doing two approximations on this equation. So here is the equation for the difference. So you linearize, which means you throw away terms which are higher order in epsilon, which means you throw away the blue term on the right-hand side, and you homogenize, which means you're replacing this variable coefficient operator by its constant coefficient. So that's exactly the notation which I used before. And then you say, because we're interested in the gradients, we should kind of beef it up with help of the two-scale expansion. And that's a pictorial picture. So you take the homogenized solution, which doesn't have the characteristic wiggles, and you use the corrector itself to kind of superpose the right microstructure in order to be a better solution of your equation. And that's, in a certain sense, the discrete definition of this martingale, which leads you from smaller to larger L, and which makes which allows to compute things. So you let the geometric factor go to 1, and then you end up with continuum equations, and those were exactly the continuum equations I introduced earlier. So that's how you actually kind of how we got the idea by first doing it in a discrete case. But now by taking this continuum limit, you have all the tools of Ito calculus at your disposal to estimate the error, for instance, you're committing in the corrector equation. And that's explained on the next slides, where you get kind of an Ito SDE for the error, for the residuum, where you really see next to this multiplicative term, where you see how the homogenization error and the linearization error enter. So you get a very clean way of analyzing the error you're committing by this proxy corrector. Okay, and so let me summarize. So the first somewhat older result is kind of getting these annealed second moments, and the more recent result is this failure of tightness, or kind of this first step towards intermittent behavior of the solution of this equation. Both papers are actually fairly short, 25, a bit more than 30 pages. So I hope that they're readable. So I think what's interesting is here the connections, right? I mean, the results certainly can and will be sharpened, but the connections that we start out with drift diffusion process in time, okay, we connect to scale by scale homogenization. This gives us a new process, but now in the cutoff scales L, that allows us to connect it to a stochastic exponential and eventually to Gaussian multiplicative chaos. And so here is one little bit of an outlook. So I think thanks to this connection, we can do much more explicit calculation. So for instance, something we want to do and partially have embarked on is, instead of looking at the gradient of the harmonic coordinates, it might be more robust or more convincing to look at the increments. So again, I'm speaking about the solution. So we're looking at a given time t, the difference of the coordinates if we start at different points. And also at the level of the approximate quantities, these increments again display the same intermittency as the gradients. So we get these unusual exponents. There should be a 2 instead of a 3, and we also see that, as to be expected, the modulus of continuity of this map is slightly sub-Lipschitz. So in line with the SPDE argument, which I gave at the beginning, that you would expect it to be a C1 minus. And in a certain sense, that characterizes this in the sense that the C1 minus, the minus is in fact a logarithm, but which power of the logarithm you see depends on the moments. And that's again like in Navier-Stokes, where you look at kind of velocity increments, you get kind of Hölder exponents which depend on the moments. Here it's the same phenomenon, just that you see it in the logarithm. So I think we have a good case for intermittency in U, but of course what we would like to understand is how does that translate into the intermittency of the original process. So the idea, at least I have, is that kind of this process is also interesting because over time it explores these rare but large level sets of the Gaussian free fields. But that's in a certain sense done probably in, at least I would expect in a fairly intermittent way. So so that I think the fact that here you get this intermittent behavior in the Lagrangian coordinates reflects this dynamical intermittent behavior of the original process, which is at this moment just an image and no proof. Okay, let me stop here.
Thank you very much. Are there any questions?
So I asked it once already. So do you think that you can step away from the Gaussian? I know all the computational part rely on the fact that your field is Gaussian, but actually what matters physically is the long distance behavior of the field and not the Gaussian structure. So it's a meta question, of course, because technically I don't see how to. I see that technically you rely on Gaussian computations, but phenomenologically it shouldn't matter.
I would agree, but now I would say that the fact that we see intermittency, even in the Gaussian case, even for small Piclet number, is the interesting. You don't need to go to something fancy. You get this behavior even for the simplest input. So I agree, it would be interesting to show that it's kind of more robust. But at this stage, I would say the interesting message is that even the simplest input, you get kind of a subtle
There are
output.
very natural examples where, for example, this 6 vertex.
Yeah, the discrete cases.
Class,
yes.
And or simpler than the 6 vertex. There are others anyway.
Yeah.
And it would be really great to understand. But
yeah, I agree.
do you use the grading of the Hilbert space? So this Hermite, so the how do you call it? So you have the L2 space, and the Gaussian L2 space is grading.
Yeah.
Do you explicitly use the grading?
No. In that sense, it's different from your and Giuseppe's method that we don't use Fock space or Gaussian chaos decomposition. I showed you, I think, what we used, and that's more this dynamical.
So I just want to, so you gave us this specific example where you are, moving in the curl of the GFF, but I presume this kind of enhanced dissipation thing so probably has some application in fluids too. No? So I wonder to which extent this whole story could be told for some fluid equation.
Yes. So one extension which I'm confident about there is recent work by Hendrik Weber with a PhD student, I think Belmus is his name, where they show that the result of Giuseppe Canizaro and co-workers persists if your drift is renewing in time. If instead you take not kind of a frozen-in Gaussian free field, but you look at the at the dynamical drift, and provided the renewal is sufficiently small, and that's the case in the natural case, you preserve this super diffusive behavior. If the renewal is too fast, then you're back to pure diffusion. So I think that kind of these intermittency results would extend to that. Now, for more general signatures of the drift, I think that's interesting. I don't know, because it might be that this problem, because it's critical, is just at the watershed between problems where you have homogenization and problems where you can renormalize a singular SPDE. And we're, in a certain sense, pushing homogenization methods in a range where they cannot really apply because the problem doesn't homogenize, but in fact that comes with a benefit. They become much simpler in the sense that you can write this strange martingale proxy to the corrector. So, so whether one is this lucky in kind of more general fluid models, I don't know, but certainly should be explored.
We have time if there's one more question. If not, then let's thank Felix again.